Hello everybody. Let's discuss the intermediate value theorem. I think it could be helpful to give kind of a real-world connection with what the intermediate value theorem says before we talk about it more formally. So consider this. Brady drives east on Interstate 94. When he passes the St. Joe exit, he's traveling 70 miles per hour. Further along his trip, when he passes the Clearwater exit, he's traveling 75 miles per hour. Which of the statements then must be true about Brady's drive? Well, consider statement A. Brady's top speed was 75 miles per hour. That doesn't have to be true, right? Somewhere between St. Joe and Clearwater, he might have sped up to pass somebody or go around, okay? So I don't think A has to be true. Similarly, B doesn't have to be true. He was going 70 when he passed the St. Joe exit, but maybe he slowed down at some point in between St. Joe and Clearwater, and then sped up again to reach 75 miles per hour. Statement D, Brady's speed was 77 miles per hour at least once. We don't know that. His speed could have stayed between 70 and 75. And to that end, statement C is the statement here that has to be true. If Brady was going 70 miles per hour and later on ended up going 75 miles per hour, well, his speed is a continuous function there, his velocity. He can't jump over 73 miles per hour. He can't go 70, 71, 72, and then 74. He had to have been going 73 miles per hour at least once on that trip. And in a nutshell, this is what the intermediate value theorem tells us. Okay, let's talk about it more formally now. First of all, when does the intermediate value theorem apply? It applies to a continuous function on a closed interval. So when a function is closed on a continuous interval a to b, that's when we can apply the intermediate value theorem. What does it say? Well, for that function that is continuous on the interval a to b, that function will take on every y value between f of a and f of b at least once. Like Brady's speed had to take on every value between 70 and 75 at least once on his drive there. Here in the image, w. Pick any w you want between capital A and capital B. The function is going to hit that value at least once because it's continuous, because it can't skip over anything between those y values. So then what do we use it to do? For AP Calculus, what do we use this theorem to do? We use the intermediate value theorem to justify whether a function hits a specific output value, a specific y value, on a given interval. Here's an example without any context to it. Use the intermediate value theorem to show that the polynomial function f of x has a 0 on the interval from 0 to 1. First of all, making sure that the intermediate value theorem actually applies here. A polynomial function such as this is continuous everywhere. So we can apply the intermediate value theorem everywhere, more specifically for this problem on the interval from 0 to 1. So then what we have to do is we've got to check out those endpoints. We've got to see where the function is at when x equals 0. We've got to see where the function is at when x equals 1. In other words, plug in 0, plug in 1, see what those output values are. Well, if we plug in 0, we're going to end up getting negative 1 from this. If we plug in 1, that's 1 plus 2, which is 3, minus 1, which is 2. So at the beginning of this interval, at x equals 0, the function is at a y value of negative 1. At the end of the interval, the function has a y value of positive 2. Well, perhaps a quick sketch would help us visualize this a little bit better. When x equals 0, y is equal to negative 1, maybe down here. When x is equal to 1, y is equal to positive 2, maybe somewhere up here, right? And this being a cubic function, it could look something kind of like that. Well, clearly, this function does have a 0 on that interval. It's got to cross the x-axis because it goes from a negative to a positive, negative 1 to positive 2. Okay, so using this information here, since those y values, f of 0, okay, that y value is less than 0, which is less than the other y value, f of 1, IVT then guarantees that there is some, pick your favorite letter here, some c, say, on the interval 0 to 1, such that that x value is a 0, makes the function equal to 0. This is what the intermediate value theorem does for us, at least in regards to AP calculus. So what's the big deal about this continuity piece? Why does a function need to be continuous in order for this theorem to apply? Well, here's a simple example. Consider a function that has a removable discontinuity, a hole in the graph. Well, all of a sudden, if there's at least one point of discontinuity, the function could skip over that y value, and now it's not meeting that conclusion where it hits every y value on that interval. So we've got to have the continuous function like Brady's speed earlier in order for this intermediate value theorem to apply. Alright, so then let's take a look at what a multiple choice question could look like. Let f be a function that's continuous, so IVT applies, on the closed interval 2 to 4, where f of 2 is 10 and f of 4 is 20. Which of the following is guaranteed by the intermediate value theorem? Now again, we can apply that theorem because we have that continuity aspect. Okay, we're told that here. I'm going to underline it. It can sometimes be helpful to just do a quick sketch of a graph. I haven't even read any of the choices yet. Okay, we know f of 2 is 10, so say that's maybe right here. That's the point 2 comma 10. F of 4 is 20. This is not drawn to scale at all. This is 420. And we don't know what type of function we have here, so we don't really know how the function behaves in between those spots. Okay, but you know, maybe it does something kind of like this. Kind of making something up. I'm going to actually start from the bottom and work my way up here. So looking at statements E and D, notice we have that prime notation, that f prime of x. This is referring to the slope of f, right? When we talk more about derivatives later on, we'll talk more about these statements. We're given information about f of x, not f prime of x here. In order to say anything about these types of statements, we need something called the mean value theorem, which we're not talking about here. And so these two statements are out. Letter C, f attains a maximum on the open interval. Well, per our earlier conversation, the intermediate value theorem doesn't guarantee that. In fact, this is something regarding the extreme value theorem, another major theorem that we'll talk about in AP calculus, but that we haven't discussed yet. Okay, so these ones are out. We have a and b remaining here. We have f of 3 equaling 15, and f of x equals 13 has at least one solution on the open interval 2 to 4. Well, let's think about f of 3 equaling 15 for a moment. Let's say 15 is, between, smack dab between 10 and 20 here. Well, right now on my graph, I have f of 3 probably like more down here, right? I don't think, and I know it's not necessary for f of 3 to be exactly halfway between f of 2 and f of 4, halfway between 10 and 20, right? We're not guaranteed this is a linear function. We don't know about that type of behavior. Okay, so this one is also out. The intermediate value theorem does guarantee for us, though, letter A. Okay, this function f of x has to hit a y value of 13 at least once on the interval from 2 to 4 because it starts at a y value of 10 and ends at a y value of 20. Like Brady's speed, starting at 70, ending at 75, had to be 73 at least one point. Here this function has to be 13 at least once on the open interval from 2 to 4. It could be twice, could be more than that, but it's got to happen at least once to go from 10 all the way up to 20. So process of elimination could kind of help us out there. This one is guaranteed by the intermediate value theorem. Finally, let's consider a possible free response question using the intermediate value theorem. The height of a tree modeled by a continuous function h of t. Not much of a sentence there, but there we have it. Selected values of h of t are shown in the table above. The question here, on the interval from 2 to 10, must there be a time t where h of t is equal to 8? Between 2 years and 10 years, must there be a time when the height of this tree is 8 meters? And we have to justify our answer, and that's key here. Okay. The way that this question is worded is really a big indicator for us that we're using the intermediate value theorem here. We are given values of h of t. We are asked if there is a t value when h of t is a specific value. Remember, that's how we use the intermediate value theorem in AP Calculus. Okay, so now in order to apply the intermediate value theorem, remember we've got to have that continuity aspect. Well, we have that. H of t is continuous, right? And when answering a free response question, we need to establish that. H of t is continuous. And so that indicates for us here that the intermediate value theorem applies to h of t. There's lots of ways that you can write that. I'm just kind of using some shorthand here. Okay. So, now that we know we can apply the intermediate value theorem, let's pick a specific window where it can help us to show that the height had to have been 8 at one point. Go back to the warm-up. We had Brady between St. Joe and Clearwater going from 70 to 75. Well, yeah, he had to hit 73 because it's between 70 and 75. So here we've got to find a couple of h values where we can kind of sandwich 8. A couple of h values that kind of border 8 or put bookend around 8. And I'm looking at these ones here, right? We've got 6 and 11. I think that we can use that interval from 5 to 7 to apply the intermediate value theorem here. So, what we've got to establish here is that h of 5, right, h of 5, which is 6 by the way, the height 5 years into this was 6 meters, okay, that's smaller than 8, and then h of 7, which is 11, 7 years into this, the height is 11 meters, is greater than 8. And so the intermediate value theorem then guarantees for us, I'm just going to say says, the intermediate value theorem says there is some time t on the interval 5 to 7, and you could use interval notation here if you want. I'm using inequality notation, such that h of t is equal to 8. Right? H of 5 was 6 meters, h of 7 was 11 meters. So just like Brady's speed earlier, with the continuous function here, the height of this tree, the tree didn't just skip over 8 meters, right? It didn't, start at 7.9, skip to 8.1 automatically. It had to have been 8, even if it was for a fraction of a second. And so we have established that by picking that interval from 5 to 7, right? I'm going to underline the key parts here in green. In order to do this correctly and get all of the points on a free response style question, we have to establish that this function meets the conditions for IVT to apply. We have done that by stating h of t is continuous. Okay. We then have to successfully pick that interval, that window that borders or bookends that specific value we want. 8 in our question here, 8 was between 6 and 11, so between 5 years and 7 years, we picked that window to apply that intermediate value theorem. There's the long and short of it, the intermediate value theorem. Thank you for watching.